Hello everyone, welcome back to my channel. My name is Dr. Mohit Sharma, and in this video we will go through the maths of LoRA, which is very popular these days for fine-tuning large language models. Okay, so let's get started. So imagine you have a very giant model with billions of parameters, okay, and you want to fine-tune it on a small data set that you have. It could be your company's data set or some other data set. Okay, so let's say you have a big model which have, let's say, 10 billion parameters, okay, and you have some small data set. Okay, this is your data set. Now you want to train this model on this data set, small, but this model is already pre-trained. So pre-trained means is that this model is already trained on a large data set. Okay, but this data set that we are using, it could be a private data set, okay, that the model is not aware of. So if we will train this large model on this small data set, which could have, let's say, 10,000 rows, okay, so it is a huge task to train this large model, okay, for this 10,000 rows. So what you will have to do, you will have to train all the weights of the matrices of this model, okay. So all of the weights you have to update, okay, but that is very laborious task and it requires lot of resources, okay. So that is not a very practical approach these days. So you cannot always train the model for some smaller data sets, okay. And let's say this is a 10 billion data set, so its corresponding weights will be around, let's say, 15 GB to 20 GB. Okay, so you need a lot of space for your GPU and you need higher VRAM. Okay, and it will take a lot of time to train. So there is a better approach to fine tune large models on some private data sets or some new data sets, you can say. Okay, so this we can do with the help of LoRA. Okay, so LoRA means low reg adaptation. Okay, so we will discuss it more in next few minutes. Okay, so basically when you do the full fine tuning, like we were talking about it in this picture, so this is the case of full fine tuning. Okay, so in this full fine tuning you change all the parameters, you have to change all of them. Okay, so it requires lot of memory. Okay, and it can also slow down your computation. But now with the help of LoRa, we will only update a small set of parameters. Okay, so let's see how we can do this. So let's say we have the original base model has some weights W0. Okay, these weights are for the base model. Okay, that we are importing from Hugging Face or from some other library. So let's say this weights has a dimension of d cross k, where d and k are very large. Okay, so the idea is we will not train w0, okay, but instead what we will do, we will add a low rank delta W, okay, with this W0, and we will only train this delta W. So let's see how we will do this. So our W is the base model plus delta W. Delta W are small weights that we are adding into our base model. We are not changing our base model. Okay. So the delta W is consist of two small matrices which are called B and A. Okay. So it is a product of two small matrices where your A has a dimension of some R cross K. Okay. And B has a dimension of D cross R, where R is your rank of the matrix. Okay, and we have in general R is much less than the minimum of D and K. Okay, suppose your D and K are of the order of 1000, so R can be of the order of, let's say, 10 at most. So your W can be written as W0 plus some parameter, let's say S, okay, B times A, okay, where S is your alpha by R, okay. Alpha is some hyperparameter and R is the rank of the matrix, okay. So this W is your effective weight, okay, and this W0 is your weights of the base model, and B and A are small matrices, okay. So in LoRa we only train this part of the weights, okay. We are not touching this W0. We will only train this B and A small matrices. So originally W0 is of has dimension W0 has dimension D cross K. Okay. So you have to train all the D cross K parameters. Okay. But now you only have to train this part which will have this which has these dimensions. Okay. So in total you will have R times D plus K. Okay. So these many parameters you have to train with LoRa. This is full and this is with LoRa. So here it is a multiplication of two very big numbers, and it is, in this case, it is only a summation. Okay. So it reduces the number of parameters by a large amount. Okay. So you can think it in this way that you are only training the 1% of your parameters of your base model. Okay. Now, after we have defined our weight, the effective weight, let us see how does the gradients flow. Okay, so we have to first express what is the output of our model. Okay, given the weights, this effective weight. So the output of the model is just W transpose X, right? So we can also write it like this: the effective weight times X. Okay, so this is equal to W0 times X plus this S B A and X. Okay, so this will be your output of the model. Like we usually do in deep learning, the output is given by y, which is nothing but w transpose x. Okay. The same way, the h is the model output, which is w transpose x, which is equal to w0x plus s times b ax. Okay. Now to calculate the loss or to calculate the gradient, we have to find what is our del L by del H. Okay, the change of the rate of change of loss with respect to the output. So let us call this term as G. Okay, so we need to find delta H. Okay, so H is given to us. Now we need to find delta H. So your DH is given as, since W0 is fixed and X is also fixed, so their derivatives are equal to 0. So we are only left with this second term. So it is S, okay, derivative of B multiplied by AX plus, now B as it is, and dA times X. Okay. So using this expression, we can write loss function or the derivative of loss function as G transpose DH. Okay. Now we just need to use these two equations, 1 and 2. We need to put first equation into the second equation. So delta S is S times this G transpose, okay, dB AX plus G transpose B DAX. Okay. So now, since we only have A and B are our parameters, so the rate of change of loss with respect to B, let's say, will be this term, right? It is equal to S G times AX, okay, and dL by dA is equal to S P G transpose times X. Okay, so now you can see that the gradients are very easy to calculate. Okay, they can be calculated by just using the product of these numbers. Okay, so this LoRa fine tuning also makes this computation of the gradients very easy. Okay, even if you don't have much resources, you can still compute it. You just need to do some multiplication, that's it. So guys, that's it for this video. And if you found this explanation helpful, then don't forget to like this video and please subscribe to my channel and also share it with your friends who are also curious about these modern AI techniques. And in the next video, I will give a walkthrough of this implementation in Python where I will use the Hugging Face library and I will do a LoRa supervised fine tuning on one such llama model. Okay. So thank you for watching and I will see you in the next video. Thank you.